All right, well, here we are in the resistance unit, unit 13 of the Adaptive Aspen Management Experiment at the biostation. This, of the four approaches to forest climate adaptation that we sought to test here, this resistance unit is based upon the premise that we can resist the impacts of climate change on forest structure, function, carbon cycling, through taking actions that should look quite familiar to people who have thought about aspen management in the lake states before. We're programmed in this region to think you cut aspen to get aspen. You remove the canopy, what you get back is exactly what you want. That may prove to be true for some part of the foreseeable future, but that is increasingly untenable, especially on sites where aspen and other climate loser species, paper birch would be a good example, are increasingly limited in their ability to regenerate, to survive, to grow to maturity or merchantability by dry soils, dry climates, other climate impacts and climate exacerbated stressors. So we were thinking about that when we designed this resistance treatment here. We chose to put this treatment in this location because of topography. We have a general north and east facing aspect. So these are the coolest slopes on the property. The soil here has a fairly high clay content in the subsoil. We are in an area where there's about a meter and a half of sandy outwash on top of a dense sandy clay loam till. And at that discontinuity, that dense clay-rich till perches the water table. So the vegetation in this area has access to a fairly stable supply of groundwater just a couple of meters down through much of the growing season. And between the finer textured soil, that groundwater table, and the cool northeast facing aspect of this site, this was the place that made sense to do a treatment intended to resist the impacts of climate change and create once again another cohort of even-aged aspen birch. We had several additional criteria as part of the specs on this sale unit. We're interested in favoring American beech wherever possible. Beech is, somewhere between 97 and 99% of it is on its way to becoming coarse woody debris. That means there's 1 to 3% of it. That's what's been found at other places, and that's about what we found here when painting the sale. About 1 to 3% of that beech seems to be resistant to beech bark disease. So we saved any disease-resistant beech that we encountered when we were setting up this 25-acre unit. We also retained mature paper birch, 1 per acre, to act as a seed source and supplement what was already in the seed bank from past seed production by paper birch. Paper birch is really the flagship climate loser species that this experiment is built around, so we really wanted to promote regeneration of paper birch wherever possible. Another spec written into the sale to facilitate that regeneration was the use of tracked equipment. The forwarder and the processor were tracked so as to scarify the soil surface when turning. This in contrast with rubber-tired equipment that does not skid steer. You get an exposed mineral soil seedbed, and I can show you one right there, a young paper birch germinating out of the seed bank in that fresh mineral soil substrate. The last aspect of the specs for this sale were the retention of 1 red oak every 2 acres. And that wasn't something I was planning to do, but the forester, Dean Reed, who administered and helped set up this sale, he's a big deer hunter. And he said that we would be fools to do an aspen removal and not at least keep a few red oak in the unit. Most of the carbon in this ecosystem is not visible to us. We can see the wood, branches, leaves. We can see the litter layer where it's present. I'll point out here that in this resistance unit that was harvested just about 2 years ago, the litter layer is now gone. The O horizon has decomposed and not been replenished due to the temporary loss of inputs of carbon in the form of leaf litter, fine woody debris, perhaps some microclimatic changes, warmer, wetter soils that we've monitored could be contributing to the loss of this O horizon compared to what we find in an adjacent unharvested stand. That's a small part of the soil carbon pool, 10% tops. Most of it is here in the mineral soil. And on the face of this pit, there's a whole lot of interesting things to talk about. In terms of carbon, the most obvious is right here. This is the A horizon. This is the organic rich mineral topsoil that forms as leaf litter, insect exoskeletons, fungal hyphae, roots, you name it, up here in the A horizon break down, fragment, and become mixed in with the mineral topsoil. That mineral topsoil is mostly sand in this particular area. As the organic matter decomposes, it generates acids that leach away things that have color from this E horizon. The E horizon, things that have color include organic matter, that's being moved out of the E, and also iron. We have a lot of iron in our soils in much of the lake states. And the iron and organic matter, they form a molecular complex that gets deposited down in this rusty brown layer. This horizon is called the spodec horizon. The spodec horizon is where true stable soil carbon lives in our spodosols. In our sandy soils, that complex of iron, aluminum, and organic matter is often many centuries old when you date it using radiocarbon. It's the free vertical infiltration of water with snowmelt in the spring that produces this translocation of carbon from the surface to the subsoil, to the B horizon. What happens here, because we're on an interesting landform, what happens next is water gets interrupted. Down here, we're in a second parent material. This top, half meter or so is sand, deposited as outwash during the last local glacial readvance and retreat. Beneath that sand is a sandy clay loam till, deposited directly by the ice. This is that water restricting layer that causes the water table to perch. This has a high clay content, relatively speaking, so it holds moisture better. This is why we have healthy 100-year-old aspen. This is why this site has the best site index in the lake states. When water hits this, it sticks around. Another thing that sticks around in the clays of this deeper B horizon, clays are very good at adsorbing organic matter. So that's another pool of even more stable soil carbon. When we've used radiocarbon analysis to figure out the age of the carbon down here, it's millennia old. It's 1,000 to 4,000 years old on average. So within the profile of this soil, there is a wide range of residence times for carbon. Here on the surface, the litter layer, the O horizon, leaves, twigs, branches, this stuff decomposes in just a few years. You get into the A horizon, there we're still exposed to the atmosphere. Soils can become quite warm, well oxygenated. Turnover times are decades to maybe a couple centuries. By the time you've moved some fraction of this carbon out of the A horizon and the E and into the B, you're looking at carbon that sticks around for many centuries. 300 years, 500 years for the residence time of carbon that makes it down this far. Infiltration of water going further down the profile allows carbon to become associated with clay minerals, the darker pinkish reddish colors here, and there that carbon can last for millennia, up to 4,000 years. I should also say some of the carbon that's moving in water downward hits this dense subsoil, this second parent material, and moves laterally. So that's what we're losing. When we're looking at groundwater, carbon transport, there's some amount of carbon that's just leaving in the groundwater and ultimately making its way probably to inland waterways in this area. In terms of carbon cycle responses, one of the things we're hoping to learn from this experiment is how the different harvesting treatments influence the mobility of carbon that we can't see. It's all well and good to measure trees regrowing, these 38-year-old aspen in a past harvest unit. That's pretty easy to quantify in terms of carbon cycle impacts of different adaptation actions. Things that are harder are what's going on in the soil and what's going on in the groundwater. I mentioned the high water table in the area of this resistance unit. We have monitoring wells where we've been collecting groundwater samples for several years before the treatments and are continuing to monitor water levels and also chemistry so that we can keep track of how much carbon is being lost from the soil, from roots as they decompose, during the flush of moisture that happens after the harvesting occurred.
I'm Katie Hoffmeister. I'm a postdoctoral researcher at Michigan Tech University. My background is in water resources. So I study water on the ground, in the ground, and see where it goes. I've been working at the biological station studying water here for over 5 years. I know where water moves across this landscape, what it does in the ground, and that's one of the things I wanted to study as part of this adaptive management experiment. When setting up this experiment, we expected there to be some differences in many aspects of the hydrologic cycle. So we expected there to be differences in soil moisture at the surface, in water a little bit deeper, and then also in what we call groundwater or shallow groundwater. We have water table measurements to assess that. We've also expected there to be some differences in terms of temperature, soil temperature, air temperature, and relative humidity resulting from our experimental harvesting. In this resistance treatment, we saw some of the strongest responses in terms of water to loss of vegetation. Here we've seen increased soil moisture dramatically right after cutting compared to our reference in our young stands, as well as to the other cut units. We also have seen really rapid increases in groundwater, so our water table levels are much higher than they were prior to cutting, and in fact we have seen surface water appear that we never saw previously. Here at this particular spot we see cattails, which we never saw prior to cutting, and we have surface water here in the middle, the very end of July, which was never prevalent before. We know that water table levels here in wells that used to be dry during the summer are closer to the surface all year long, and even have ponded water in the spring and in the fall, which rarely, if ever, happened prior to cutting. We expected that this unit would have an increase in water table and soil moisture as a result of vegetation loss, primarily because here there's relatively shallow glacial till close to the surface, so within 2 meters of the soil surface. We know from previous studies here that parent material and landforms are pretty much the dominant control on water movement in this system. So we know that here there is shallow till relatively close to the surface, and water ponds up above that till and can reach the surface when there's lots of precipitation or less transpiration. In other cutting units, we know that they're primarily outwash, so have much more permeable soils that drain relatively quickly and don't provide restrictive features to allow water for perching. So we didn't expect to see great increases in especially groundwater in those units, but here we hoped that there would be water present, which was part of the decision-making process about what this treatment particularly would become and what our goals were.